Alright, good evening. Welcome to the second video in the analysis section of our student experiment. So I have here the worksheet that we were working on the previous video. I have tidied it up a little bit just to sort of show how I would set out the processing to help communicate this sort of understanding to get that maximum analysis mark. So I'll just go through the worksheet here to begin with. Firstly, we have up here, here's the raw data. We had that before. Here's the average, the absolute error, and the percent error. So we saw all those trial values, we saw the average and the absolute error get calculated, and we saw the percentage error get calculated. Now I've added another column here, average t-squared. I'll get to why I did that in a little bit. We went through and processed our data to get rid of outliers in the previous video, and so I've actually just copied the outliers over, and the reason I've done that is, the data without the outliers over, and the reason I've done that is so that it's a lot easier for me to do the calculations on. So I've just copied trial 1, 2, 3, 4 because the maximum I had was 4 trials after removing an outlier for 4 of these things, and then trial number for the drop height of 2 meters. We can see that there's a blank cell here. Notice our fixed average does match what we had in the previous video. It's if you calculate an average and you do an average of 4 squares where you have 3 with numbers and 1 with just nothing, it doesn't treat that as a 0. It just doesn't consider it at all. So the way that this is working out, this number here, the 6.65, 0.665, it's going this plus this divided by 3. If I was to add a 0 there, and we can see that the number does change quite a lot. So now it's gone this plus this, and then divided it by 4 to get that number. So let's delete that. Okay. I have here my fixed error, I have my absolute error, and I have my percentage error in my fixed numbers. And we can see that our percentage error 2, 4, 4, 1, and about 3, compared to over here 7, 9, nearly 7, 12, and 6, nearly 6. I've also got a fixed t-squared, so I've taken this average and squared it, and I've done some percentage errors for that, and we'll look at that in a second. Now, as I said in the first one, you have to have, when you do processing of your data, there should be some theory backing up why you're doing it, and you should communicate that to us. This theory should be appearing in your rationale for one thing, in terms of saying, well, this is why we expect this relationship to occur, especially for physics, chemistry in some regards, depending on what sort of area you're looking at. You may not need to do processing of data and sort of squaring it or taking a logarithmic curve or whatever, however it will probably pop up perhaps in Unit 3. Biology may be slightly less common. So I wanted to do a quick bit of working out, and this is a little bit more physics, so feel free to skip forward on this. However, it's something that's important. So we have here in our experiment, we have displacement and we have time, and we know we're trying to work out acceleration. So we have an accelerating system here. So by looking at this, we need to think, well, what formulas govern this relationship? Now, the one that we have here would be that S equals ut, initial velocity, times time, plus a half at squared. And we're able to go, well, this number here doesn't matter because we should be starting with a u equals 0. And, anything times 0 is 0. So then, really, our final equation should be S equals half at squared. And since we're trying to work out A in this case, and A is our gravity value, we can see here, well, S, it must be related to t squared somehow. So that's going to be the linear equation we want. And so that guides me to say, that's what I need to do to my data. That tells me what processing I have to do. Okay, so you've got to use your theory to help guide it. And if I was to say something like, well, maybe I called this equation 1 in my rationale, I called this equation 2 in my rationale, I could turn around and say, well, according to equation 2, S should be proportional to t squared. We would use something like S is proportional to t squared when we're mostly talking about linear type things here. And that would give me my justification in order to do this step in the analysis. And remember, that's that difference between your 5-6 region and your 3-4 region, because you're looking for purpose or purposeful analysis about why you're doing these things. So if we go back to my graph here, we've got down our graph two things. We have S as a function of t. We see that was 99% correlation. Like, you could sit there and go, that's a really good number. I like that number. And if you did 2 divided by, 2 times 4.3, which would be our conversion, we go, oh, 8.6, that's pretty close to gravity. However, this would be wrong if we were to use this graph as the judgment call for our determining gravity. You would end up with in that 1-2 region, because you've not used appropriate theory. Okay, in fact, you've used theory incorrectly, which is a little bit worse than just missing something out. So I've plotted here 2 graphs. I've done t-squared for my average, and I've done t-squared for my clean average. And I've made 2 graphs. Here I have t-squared, and there's some error bars, and I'll go into that in a little bit, with a gradient of 3.97 and an r-squared of 98%, which we can see is less than that, but it's still pretty decent. And over here we have, for our data without the outliers removed, a gradient of 3.9 and an r-squared of 0.96. Now, that basically tells us, well, that has a better correlation than that, so we were sort of right in removing those outliers. But however, the gradients are not particularly different. This one is only a little bit lower than that, so it made it a bit tighter, but didn't significantly change the result that we got. Now, from this, going back to here, remember that if you're doing this by numerical and you need the gradient to work something out, remember y equals mx plus c. We would explain how this matches up to this, and so if my x is t squared and my s is y, then my gradient here would be equal to half a. M equals half a. I know we use m for mass. It'd be great if we just had one letter for only gradient, but g's kind of used a bit. And so the acceleration should equal 2 times the gradient, and you would explain that in order to get full, purposeful, justified analysis of data. Now if we go back to my things here, I have my 2 values. This is the gravity from the average t-squared. This is the gravity from the clean t-squared, and we can see this one is a little bit closer to true. We need to get to 9.8. We only got to 7.9, and we'll look at how to interpret this number in terms of communicating it. Now, one of the things you have to do is error bars. Okay. Now, I have gone through and worked up my error a little bit here. So I have my fixed t-squared, and I have my percent error. Now, if we look at percent error for t-squared here, and percent error for my average, we see that these numbers are twice as much. Okay? If you are squaring a number, you need to double the average. It comes from using the relative error formulas, where the relative error in something is equal to the addition of any relative errors you've calculated with. In Year 11, we're certainly more than happy to sit down and work these through with you to help you sort of get your way through, because it will be the sort of trickier part. And unless you do a lot of practice with error, it's not going to come fluidly to you. I've calculated now the absolute error, because this times this will give me the absolute error. Remember, relative error is the absolute divided by the actual number, and so if we multiply these two together, we'll get the absolute error. And I've also got here my error in my x. Now, the way as I did this method, as I said in the previous video, was myself and another student with a measuring tape dropping a golf ball, from different heights. Now, I think my error was probably about 3 centimeters. Could be more. We'll get to that in a minute. But, you know, I just used 3 centimeters. Now, I can't show you on this because this is an old version of Excel. However, you can see here they have error ranges. So the horizontal ranges, because this is the absolute error in my in my time value, is quite a bit larger than the error in my x, my displacement value. Sorry, that shouldn't mean error x. It should be error in distance or error in y. So I will correct that before I upload this PowerPoint for you to work. Excel sheet to look at in your own time. if you update to the most recent version of Excel at time of recording this video, which I believe I will take a quick look at what version it is. And remember, as a student, you can get that for free. You may have to, I've seen some students have issues where you've had Windows S mode enabled, which is like a security mode, and because then we're not getting it through the App Store, but you're getting it through the student portal instead, you need to what's the way I'm trying to explain that, you need to disable that S mode thing in order to get that on. I believe the version I'm using at the moment is called Office 365. Let's see. But it's not giving me a nice easy, oh yes, this is the version that you have. So try to update to later. I have noticed if you can see the autosave on it, then you have the most recent version. Okay. Now, if you then click on any of these data points, unfortunately I don't believe it will show it for this one. In the most recent version, you'll get a little menu bar that pops up down here. You're then able to select the chart elements, and you can add error bars. You click on the error bars, you follow the arrows down, and under custom values, you're able to select what numbers you wish to add, which numbers you wish to add as your error bars. That being said, there is a applet that we have that will do this for you. So you do still need your numbers for your errors. However, there is another app. This is the 3-line graph tool that I've talked about in physics that will generate this for you. So I have gone and placed the data in. I haven't bothered with headings and stuff, unfortunately. But again, I have the same thing, t² across the bottom and displacement up the vertical, and I've put in those error values, and you can see here we have a average gradient on that is again about 3.98, and we have our places with our error bars. Notice there's a key here saying maximum and minimum trend line. Because the errors are so weird on this, it can't automatically draw it for you. So in that case, if we were to do 3-line error bars, you would have to do them manually. It's not particularly difficult, however, it can be a little bit finicky. So for example, especially in terms of getting a value for the gradient accurately, because you're going to have to kind of do it by hand, and that can be troublesome. So there is another tool, and that's the linear regression analysis tool pack. There is a Word document that I have placed on the physics resource, and the biology and chemistry students should be able to get access to it through your teachers, and it will show you how to do linear regression, which is what this is doing, and give you an error in your gradient. So you don't have to do this. It's nice and pretty. This number here, this thing here, this big weird looking thing, will also do it for you. So you do have to have your numbers on the what's what I'm looking for. So my drop height and my fixed t², you should have the numbers on a sheet so that you can work with this. I would normally just do it all on one sheet. I've just kind of separated it up a little bit for you. And what this has done here is it has done linear regression, the same thing that gives us the gradient of these y values against these x values. That's what I've selected it for. And the numbers we care about are these down here. At least for this experiment. The x value here, here's my gradient, which you can see 3.9716 matches up to this, 3.9716. So it gives you the same number. However, it gives me the error in the gradient in this case. And I can use that error in order to work out what my range of values is going to be for calculating something at the end. So if you need to use your gradient for something, or you need to compare gradients between different data sets, you're going to need these two numbers. You might get it through doing the 3-line graph system, and you've seen a similar type of question in the data analysis exam. However, you may wish to do it this way instead. And I'm perfectly happy for you to do this. To me, this is still valid analysis. Just because you don't have a pretty 3-line graph and you've had to do things manually to get this number. If we had data that was a bit cleaner and we did get the two gradients and then we worked out the absolute error in the gradient, we'd get this number from it. So they do the same thing. So I've worked out the relative error in the gradient, and that's just this number divided by this. Relative error, remember, is absolute error divided by the real number. Here's my value for g, and I've got that by taking 2 times the gradient, like we saw in the theory. Then finally, the error in g, which I've got from the relative error times the true value, and that gives me the thing. Now, I can go lower, 7.9 take away 0.6 is around 7.3, but that's further away from the true value. We want to get close to 9.8. So I've only cared about the max value, and I'm looking at the difference between that. The reason why you can do this is while I have calculated g to be 7.9 from this experiment, there is an error in my method. My method has calculated g somewhere between 7.3 and 8.5. Okay? So I can use any of those values in there to compare it against it. Now, I can't compare there's no point comparing the minimum value. I can compare the value that I did calculate it, so 7.9 compared to 9.8, and so I would have a difference of nearly 2. But I can also compare the maximum value. So I've done that. I've compared the maximum here to say, well, how far was I actually off getting close to this thing? Now, oops, apologies. When we do an experiment like this, both when you're trying to confirm a true value, both the words accuracy and precision are important. If you're not trying to confirm a true value, the only word that's really important is precision, and whether your method has given you a precise result. If your precision is very low, for example, this is about 8% precision, which is what we got from that relative error up here. That's not amazing. It could have been a bit tighter, but for the technique we use, it's okay. If we'd used a what's the word I'm looking for? If we'd used light gates, then we'd probably have a much better precision. What I've got here is going, well, the error, okay, how far off is just the difference between my calculated and my true value. And then I have divided these to get the percentage error. So how far was I off divided by the true number gives me this percentage here. And this is my accuracy. That tells me how far off I was. So looking at that, I could say I would be 88% accuracy, or I had a 12.5% inaccuracy. I was 12.5% off the true value. So in terms of accuracy, it's not that amazing. If I'd been 5% off using, say, the average, that would be pretty okay. And I definitely want the true value to fall within my error bars. That would say that I've done both a very accurate and a very precise methodology. In this case, I would say the precision is mediocre and the accuracy is not great. And so that allows me then to start talking about limitations of my method and why maybe I have this. For example, if I think about my data, if my displacement was 0, my time should be 0. So if I go back to my trend line here, well, if I take this trend line and format it, my intercept should probably be 0, 0, because if time equals 0, displacement should be 0, because at 0 distance, if something is sitting on a surface, it doesn't take any time to fall. When you have theory backing it up, you can make that decision. And now if we look at this, we get a value of 4.5. And if that value of 4.5, 2 times 4.57, it puts us at around, what, 9.1-ish? Okay? And yeah, 9.1 is getting a lot closer to our actual value. However, you can see here that the R squared got a lot worse. But it does allow us to now look at it and go, well, this number here is a little bit weird. Maybe if I got rid of that number, things would be a bit tighter on this. Perhaps that whole data point's an outlier. However, that's kind of getting a little bit too nitpicky nitpicky and trying to go, well, let's just make it as clean as possible, and you don't want to do that. Okay, sometimes errors are going to be there. There is not much we can do about that. We just have to kind of roll with the punches and see where it goes. Now, I will put a graph with a fixed intercept so that you can see this again. I'll also on here on sheet 3, I will move this around a bit, but I'll do another linear regression next to this and put what I get from here, so you can look at the x value and the coefficient, the gradient, sorry, the error in the coefficient, in terms of if I do fix it to be going through the intercept, because you can do that. You can select should it go through a particular point. In this case, we'll say for 0, 0. Okay. So, this video has looked at a couple of more advanced analysis skills that you should be considering doing, especially with binumerical data. So you should be doing linear regression in order to work out errors in your gradients, or you should be using the 3-line graph tool, right, which I know for physics is available on the e-learners. I've placed it there. If you want it for chemistry, feel free to ask Ms. Gantamura or myself. We can help you out. But you can use this tool if you'd prefer to get a visual representation of your data. Now, if you want to use this and this at the same time, no worries, not a problem. However, it's not going to tell you anything new about it, unless your data is quite clean, well, not clean, but broad. The error bars are broad enough that you can go, well, we end up with a nice pretty 3-line graph where we have another line going this way and another line going this way, and then you've got 3 gradients to work out the error in your gradient. It's going to be a little bit messier. When I have worked with data where I've been able to use this tool accurately, or appropriately I should probably say, the number I got for the gradient error was close enough to this that there is not a real big difference. We're talking an error of less than 1%. So don't feel that I've got to use this particular graph one. I'm perfectly happy if you end up graphing something like this. You've got your error bars on it. You've got to have your error bars on it. And I know biology, you do not do dot graphs with error bars, but physics and chemistry you most certainly will. I'm quite happy for you to have a graph like this and then see linear regression type things in your analysis, okay? And you can just say, see Appendix 5 for linear regressions for the different things. Make sure you put headings on them, help out, so that if we need to go and check that you've read it and put the right number in, we can see it there. However, it doesn't have to be overly complicated. Choose the best thing to do. Now, as a final note in terms of how do we do analysis, at the end of the day, explaining you how to do analysis is like trying to explain colour to a blind person. Unfortunately, while I can show you some basic techniques and the core skills you're probably going to need, every experiment is going to be different and you're going to have to figure those things out. We will certainly sort of prompt you along with questions, but ultimately you're going to have to ask yourself, well, have I interpreted this data appropriately? Are there things I could be doing to this data in order to show better meaning? Is there any processing I can justify according to theory so that I can see relationships cleaner? How do I do this? And it will just have to take experience and time. So it is important that you do these early as possible when you're doing an experiment, so that when questions and problems arise, you've got time in order to ask them and try to sort it out. Okay. So next video we'll sort of look at discussing errors and limitations, and then that should probably be the last one in the series. Might be one more, but I think that would probably be the end. All right. Thanks very much for listening. Have a good night. Bye.